Thank you. My name is Brayden Lipscomb. I'm a chemistry and physics double major from West Virginia University. And this summer I worked alongside Dr. Henry Housekeeper and Lord Barbarian on the vertical structure of the aquatic light field based on a half century of oceanographic records from the California current. So let's just go ahead and dive right into that. So I want to start by emphasizing the importance of light in most ecosystems on Earth, and that a lot of things like the bull kelp found in the California currents and phytoplankton found in every major ecosystem on Earth, or every aquatic ecosystem on Earth, use light to do photosynthesis, to create energy for themselves and oxygen for us to breathe. And so it's important for light to penetrate through the surfaces of the ocean and the different layers as the ocean is stratified. This stratification of the ocean leads to differences in the aquatic light field, as pictured here. The aquatic light field is it's the logarithmic decay of light as it enters through the surface of the water. And due to the stratification of the ocean, individual locations in the ocean, known as stations in which data is taken, will change the way this aquatic light field moves and looks, as it might shift where light is fully attenuated or extinct, meaning that light is scattered and absorbed. And yeah, let's move forward as I'm going to talk about a little bit of background research I did as I entered into doing this research. First, satellites only observe the surface level of the ocean, and so they can only really see things just on the surface using surface reflectance off the top of the ocean. And additionally, we can build models that these satellites can use to dictate different types of near-surface structure using surface reflectance. And finally, these models can, with lower complexity and more uncertainty, lead to, of course, less certain results. But the most important factor of this is understanding depth. And so to know about the structure, you must know which depth you're trying to find information on. And so that leads me to my question: how well can we know subsurface light only knowing surface light? As the literature that I'd read explained that a lot of uncertainty with other values leads to uncertain results. And so it's important in the current demographic oceanographers, optical oceanographers, that you know more than just light and depth, but I wanted to observe what the relationship might look like with only those two factors. So I'm starting with my data set known as CalCoffee. CalCoffee stands for California Cooperative Oceanic Fisheries Investigations. It's a series of cruises off the southern end of California that go to different station IDs, as I was talking about before, and take data there. And I specifically used the bottles data from their database. And the bottles data is taken off of the Rosette sampler, pictured here. It has a series of bottles that are slowly lowered to the ocean and close the caps to take the composition of those specific layers they're looking at. However, I did not use the data from the bottles. I used the data from the PAR sensor pictured here on my excursion to biospherical instruments, and I would like to thank them. That was a great time. And what the PAR sensor is, it means photosynthetically available radiation, or the radiation that is available to be photosynthesized by organisms with chlorophyll. And from this database, I used only two metrics: the depth of the bottles in meters and the light percentage. As light we take from 100% of the light that enters the surface, and as you go deeper and deeper, you start to observe different percentages of that light comparatively. So let's go over some of these data products that I used. First one is KD-PAR, which is the downward attenuation coefficient of photosynthetically available radiation. And what that means is that this is just our example of our surface value. And I'll go over how I calculated that in a minute, but just keep in mind that this is what I'm considering my surface value. We also have our E-folding depth, which is the depth at which light is 36.76% of the light that entered the surface. And then we have 10% depth, which is the depth at which 90% of the light is removed from the surface, 1%, 99% of the light is removed, and 0.1%, where 99.9% of the light is removed. And these are my 5 data products I will be using to compare subsurface and surface light values. Now, how did I come upon these? So this is another graph of our aquatic light field. And what I did with this is that I first did a log linear transform, meaning that I took the log 10 of the light intensity values and plotted those once again against my depth values to get a more linear line so that I can interpolate my data products from these points. So I looked at points above and below in depth, my specific light intensity values, and that gave me, using the slope, the values in depth from the raw data. Additionally, once I did that, I had to calculate KD-PAR. So I interpolated the light percentage at 5 meters depth, and then looked at the coefficient of attenuation, or essentially the log linear slope of attenuation, between my near surface value, which is 0 meters depth, and my shallowest observation, which I'm considering 5 meters depth, simply due to the fact that my data set would not allow me to do anything greater or lower than 5 meters depth. So, moving forward though, I would like to talk about some of the limitations with this data set, or in the way that I went about this. Observations of light intensities are opportunistic, meaning that the rosette sampler doesn't always carry the PAR sensor, and so I only have around 1,900 station IDs that work for using KD in these light intensity values, where there are around 40,000 different ones since 1984 to today that are for the regular bottles data set. And so I have a very small number comparatively to the number of bottles data. Additionally, the instrument has a low resolution of around a meter. Anywhere within the meter that is posted on the data set could my light intensity values truly be, and we'll go over why that causes a lot of variability. Additionally, there's a lot of context missing around this, the measurements, so I could be within the ship's shadow. There are a lot of things that could deal and affect the way that I observe PAR. And finally, we are only considering physical parameters here. In this study, I would like to look at biological parameters in the future, but with the data set I was currently using, there was really no way to go about doing that. So let's just look at some raw data right here. This is just to show you that the log decay happens across all of my data set, and there is a lot of variability here as I'm showing you all of these different values. And that has a lot to do, once again, with the missing context surrounding this, but also due to the stratification of the ocean. So with that all in mind, let's go ahead and look at some real data, some data that I interpolated. So we have our subsurface coherence plots trying to establish the relationship between my subsurface depths. So on my x-axis here, I have the natural log of the e-folding depth versus the natural log of my 10% depth. And then I have 10 to 1 and then 1 to 0.1. And as you can see, I have R-squared values ranging from 0.78 to 0.98. And so this shows a very strong linear relationship between these two values that increase with depth. Now, this increase comes with the fact that as you get lower and lower, due to the fact that light will attenuate faster, we have depths that are closer together right next to each other. So like, for example, 10 and 1 are pretty close to each other as comparatively to the e-folding and 10% depth. And additionally, please take all my values of 0.1% light with a grain of salt, simply due to the fact that I only have 27 values comparatively to the 1,000 or 1,900 values within these other two graphs. So there is some kind of strong, coherent, linear relationship between my subsurface values. So let's look at surface to subsurface. So in my x-axis, I have log 10 of KD par, and in my y-axis, I have my log 10 of my depth data product. So e-folding, 10%, 1%, and 0.1%. And these R-squared values range from 0.88 or more trustworthy 0.79 to 0.51. And these also show a convincing linearity between themselves, as you must remember, I am using very low resolution instruments, and I'm also only comparing the physical parameters, but I'm still seeing some kind of linearity in this. Additionally, I will say that there are some weird little stretches of lines that cut through my lines of best fit, as found in these three different graphs. That could have a lot to do with something that might be happening in the ecosystem at the time. These are probably values taken around the same time, maybe the difference in methodology in the way that the PAR values are taken. I don't really know, because once again, I'm missing a lot of the context that surrounds the values being taken. So moving forward, I would like to talk a little bit about my primary findings, in which once again, there seems to be a stronger relationship than anticipated between subsurface and surface light values. And with this in mind though, potentially there are ways to improve models and our understanding of the vertical structure of the aquatic light field using satellites and using this in situ data to make these comparisons. And finally, I would like to go over some of these caveats. Once again, I'm not using any biological parameters, so there's no comparison of the physical light values to chlorophyll values that you might find in the papers that I have discussed in my background. Additionally, there are inherent deficiencies with my PAR observations, because once again, I'm missing context. These are low resolution instruments. The list could go on and on for reasons why there are deficiencies. Additionally, my derivation of KD PAR is also missing context, as there are different ways that we can account for near surface effects or dissimilar depth sampling resolution. But overall, I feel as though my results are pretty profound. So just once again, all of my data products were taken from the CalCoffee database, and that they were interpolated using the raw data that I got from that. My subsurface data products indicated a coherent log-linear relationship, showing that there is a way to make comparisons between the subsurface data. But that, of course, comes with the caveat of you have to use in situ to observe the subsurface directly. But when you look at near-surface light observations, and you can correlate those now to subsurface light availability, the aquatic light field becomes a lot more clear if this were to hold true with a bigger data set, which is where I want to move into future works. Potentially, I could use in future works this to improve models on remote sensing, such as satellites. But additionally, I would love to look into using Argo floats to compare these light values, as the Argo floats are a network of around 4,000 free-floating instruments that take profiles of the oceanic columns. And while not all of them have fluorometers or PAR sensors, a lot of them do, and which would allow me to increase this data set by a very large factor, as while there are only 1,900 here, there would be maybe 2,000 instruments that have been working for a number of years now, and I could use this to better understand the physical relationship that the aquatic light field has, as well as comparing it to biological parameters. And finally, I would just like to thank the many people who have helped me on my journey here, and the many people who have helped me in my journey while I've been working here. So Dr. Henry Housekeeper, Luri Barbarian, Dr. Deshaw Sardana, the Oceans crew, my friends and family back home in West Virginia, and my research mentor, Dr. Fabien Goulier, and I'm now open to any questions. Yes.
I'm sorry if I missed this, but on your PAR graphs, you used a whole bunch of different colors to represent the different dots. Was there any type of symbology or meaning to that?
No, it mainly just comes from, we called them confetti plots while we were working on them, and so they were fun to just keep this way, as they really don't represent anything else. And it would be harder to tell them apart, like this solid linear line, if they were all one singular colored point. So it makes it easier to differentiate between the spread and everything. Yeah?
I know you had mentioned not utilizing biological factors and why light attenuation is changing with depth, but did you happen to look into what factors, whether biological or not, change that?
So yeah, like I was talking about before, the stratification of the ocean can lead to differences in chlorophyll concentration on different levels. So when you're comparing different depths, you're also looking at the overall chlorophyll concentration at those depths, and that can lead to more or less scattering or more or less absorption, so a stronger or weaker attenuation factor. And so that's why I think the papers that I was talking about before, the problems that they were having came from a lot of the biological parameters that leaded to more variability or scatter within the data. Yeah.
I'm sorry if I missed this, but I know in the winter months when there's more storms offshore, we see stronger winds that can lead to upwelling with more nutrients, which I was wondering if you knew anything, if that had any effect on that light, and if it changes seasonally because of maybe upwelling or other factors, or if you looked into that at all?
So that would have a lot to do with the biological factors. I am only comparing light intensity to depth values, as I have no way of making statements on overall chlorophyll levels or the way that nutrients would affect the stratification. Yeah.
Sorry, great presentation, Brayden.
Thank you.
Sorry if I missed this, but what is E-folding?
So the E-folding depth was just one of my data products that represent, oh God, I keep on doing that. It represents the light percentage at 36.76%. So it's just, the importance comes from, it's found in a lot of optical oceanography papers, as well as the rest of these percentages. So it's just a standard within the field that I'm using. And it's just called E-folding because it is the light being reduced by a factor of E. Yeah?
Just a follow-on to that. Some of the groups have talked about lifetimes of gases in the atmosphere. And lifetime is also E-fold.
Oh,
so,
awesome, yeah.
So when you go from 100% a lifetime, it doesn't mean it's gone. It means it's decreased to 36.76. Yeah. So it's, if you, on a calculator, there's like an E button. And if you hit it, it gives you 2.78 or whatever. I don't know. But if you hit one over that, it gives you that.
Awesome. My E.
Thanks, so.
Yeah, what's up?
So I'm curious if the overall goal for modeling this kind of things is to observe the subsurface light field from satellite measurements, and just kind of what the applications of that would be.
So yeah, it would help us understand, like you just said, the subsurface structure of these oceanic columns by looking at the reflectance from the surface. And the applications come from being able to better understand the types of life that exist under that. So like looking at the chlorophyll structure, like talked about in, I keep on doing that, one of the background papers. I didn't spend too much time on it, but I really wish I would have the time to do that, as this one was really interesting, talking about comparing surface chlorophyll to the near surface chlorophyll that exists under the water. And additionally, this one talks about looking at even larger subsurface structures by looking at surface chlorophyll and irradiance. Hmm? Any other questions?
Thank you, Brayden.